Okay, let's check. We were on this page, will be? Okay. We entered here the last time. I make a label because quite a long time ago. So the last lesson that we had was on 20th January. We ended here. Now we want to actually look into this, finding limits using derivative. I want you to realize that what we are doing here is we are actually learning another way to compute limits. In chapter 1, right, we have already learned several methods. Tell me one method that you know of to find limits of a function. We simply just plug it in. True or not? Yes. What's another way we did to find limits? We actually use conjugate, right? By conjugate. What's another way that we find limits? We actually factorization. Okay, yes, you're right. Squeeze theorem is another one. There was another thing that we did for finding limits, and that was the use of x over sine x. You know what I mean? So we have several methods in chapter 1 to find limits. In chapter 2, limits persisted in chapter 2, just that in the context of differentiation. Alright? So in the context of differentiation, we learn how to find the derivative of a function at a point from first principle. And I pose a challenge to some of you to work out e to the power x from first principle. And you realize that it's not that straightforward.
I reached the point where I need L'Hopital rule.
Right.
It doesn't work.
You should not, you cannot, if you don't use L'Hopital rule, you will actually like
defeating the purpose.
Yeah, cannot. Okay, so now moving on in this chapter, we now want to understand that in using the definition of differentiation, we can actually use it to find the limits of some function. For example, in this good example, square root of x minus 2, of course, you'll tell me you have a way to doing it now, but doesn't matter. Let's see how come it is equal to this. The reason why this limit on the left side, this one, right, is equal to this is because we have actually understood that the definition of derivative is limit as x goes towards 4 in this question, right? Because you are differentiating root x right now. So what happens is you'll be root x minus over, and you realize that this expression is exactly the very thing that you want to find from the start. And because of this, we now capitalize on this fact and now work out the limit of this function using the derivative of root x and evaluating the derivative at x equals to 4, and we get a quarter. Right? So this is interesting because we are now doing the reverse. We use limit to define differentiation, and now we have established that result. We are now doing the reverse engineering, understanding differentiation from the definition of limits. We now use it, use derivative or differentiation to actually work out the limits of some function. It's quite clever, right? Likewise, for example 10, let's pretend that we didn't have the result 1 in the chapter 1. We're going to do it from ground 0. How do you do it? No. To do this one, right, you want to see this as like that. As theta goes towards 0, sine theta sine 0 over, and because you are able to write in this manner, you begin to realize that this is simply the differentiation of sine theta evaluated at theta equals to 0. And we all know how to differentiate sine theta, didn't we? Don't we? We know, right? It is cosine theta. And to evaluate cosine theta at theta equals 0, we all know that cos theta is going to be 1 at 0. So example 10 and the earlier example demonstrated to you how we can capitalize on the definition of differentiation to work out limits. So that becomes another way to evaluate limits. Before the end of chapter, there is going to be another way. And in the third chapter, there is going to be another way. That means you're going to learn L'Hopital at the end of chapter 2. And in chapter 3, in integration, there is also another way to find limits that you're going to learn in chapter 3. So along the way in chapter 1, 2 and 3, you pick up different ways to evaluate limits. And bear in mind, limits is the foundation of calculus. No? Then you must have mastery over it, which we already have because you did chapter 1, right? Say yes.
Yes.
Okay, thank you. Let's do 2A. This is exercise A. For the case of exercise A, you're asked to find the limit of this function, and in particular, we want to try to capitalize on the definition of differentiation from first principle. We are going to write this thing as limit x tends to 1. I hope you know how to rewrite this thing as right. So what I've done here is I have rewritten the function as a product of these two. Why do I do this? Is because I then want to actually break up this one into the product of the two limits. And we know that this is possible because we know that prematurely. This is not too bad. This is going to be 1. For this one, by the definition of differentiation of ln x evaluated at x equals to 1, I know that the earlier limit is just like that. So this becomes 1 times 1 over x evaluated at x equals to 1. So that's 1. So I have done part A, right? By capitalizing on the definition of differentiation. Okay. Alright, that is actually part A. For the case of part B, we are going to do it similarly. And the thing about such question is, you need the good eyesight. Okay, let's test out again. Let's see. Arohi, right? Arohi, right? What do you think B is? Written as a differentiation, what would it be? What is the function do you think? Do you say x to the power 7? That x is what? Arohi? Right, you're right. The ability to see this line is for you to be able to think reverse. If you think reverse, the blue color, by definition, it becomes the limit of that thing. So whether or not you can see the blue color, right? It really depends on whether or not you have good eyesight. Then you say, I can't see. I'm say to you, then see again. Still can't see. Then see again. And then you just toy around with it. Eventually you get to this.
You might half plus x, the entire thing to the power of 7, x equals to.
And therefore it's x power 7, is it?
No, we have bracket half plus x, the entire thing to the power of 7, and then if x equals 0.
I don't understand.
And EDX and that under this one.
Okay, you don't have to know because you can see this one as the equivalent of this formula, no? Limit h goes to 0, f of a plus h minus f a over h. You know, you see it like this, it's easier, and it's easier. Right? If you compare part B with this way of writing a derivative, then you will more or less be able to see.
Yeah, I realized that, but I didn't do it that way. But, yeah.
Okay. So with this in mind, right? With this in mind, this becomes 7x 6 x to the power half.
Really no difference.
And then this gives you 6 4. It is part B. So as I write now part B, would you want to try fully digital the next chapter? I'll give out the PDF version of chapter 3, and then you'll bring your PLDs to class and write on the PLDs. So you say yes, she is no, you want to embrace technology, no? Because it's easier, you don't have to carry books, you don't have to print notes, you have everything online, rather on your PLDs.
I like books.
You like books, huh?
I like books.
Actually, I'm gonna share with you, at the same problem like you and you. I try not to do that, but in recent time, I begin to realize that there's a lot of advantages. I can actually archive it very nicely. I can organize it nicely on my folders. I can have different colors. I can erase it nicely. I can do wonders. I can even do recording. So, class, I like to urge you to actually make a mindset shift. Be brave to embrace the whole new world of learning. Okay.
It's expensive.
You have a PLD, sir.
Yeah. And it's
Okay, for
I
part
don't
C,
like it, and I don't like using it.
for part C, right? For part C, let me do part C in this manner. Let F. Okay, if I define a GT, if I define a GT to be this. Okay, I'm going to write this way. Okay, I let this integration of cos t square to be gt plus c. Can? Okay. I start off for part C with this sentence. So if that were the case, then my part C will be like this. Limit x goes towards -2. If the integration of cosine t squared is gt, then this immediately becomes g of x minus g of -2. And then write this as x minus -2. Right? Then immediately you see that by the definition of differentiation, this thing becomes what? The differentiation of gx evaluated at x equals to if this is like that, okay, then what is the differentiation of gx? Up. Right. And this seemingly hard question is done. Nice. Right? In the other class, they told me they tried, and then they say, well, very hard, very tedious, and new to them. But actually, it's not too bad.
It's just the inverse of a function. It's a function. It's a function of an inverse function, which you get basically the original.
If you see integration is the inverse, if you see that way.
Because it is what?
It is. The reverse of differentiation. Okay, so nice, right? I beg pardon? Will we be able to integrate cosine x squared?
Yeah.
Okay, so class, there's a question raised, no? There's a question raised. Are we able to integrate? And the answer is analytically no. No.
Why?
没有.
Why?
But if I put in an x by the side, yes.
Yeah, this one has yes. This one has something like this.
But like that alone. The truth is, there are a lot of functions under the sun that we can't integrate in. Yeah. That's the truth. There are a lot of equations under the sun that we can't solve by hand. A very simple equation like this. Apart from 0, the rest of the solution are not easily found. Not easy. So, in case you live to think that you have reached high school math, you can do everything under the sun. The truth is, the more you know, you realize that the more you don't, That's a paradox.
Okay, so definitely many solutions, but you don't know where to choose.
We can't work it out by hand.
You can work it out by graph, but not by hand.
We can only find approximate solutions. You will learn in year 6 techniques to find approximate solutions to equations that we can't solve. Maclaurin, do you say Maclaurin? Okay. Maclaurin series, if you say, for example, this one, right? What do you need to do? You want to expand this as Maclaurin series. Are you saying that? And then after that, use it to solve. Not good enough, because when you solve it this way, you are getting solutions that are near 0 only. Solutions that are not near 0 won't work. Because Maclaurin series, unlike the other one, the Taylor series, right? Yeah. But even that, whatever you use, the series will not be helpful. In numerical methods that you learn in year 6, you are able to find the solutions up to the accuracy that you want. Okay, that's in year 6. Okay, look at this page, differentiability of inverse function. Take a good look. Sure. Okay, let's go ahead. Okay, on this page, right? On this page, it's quite heavy reading, because I'm not sure if you understand what they are trying to say. But the basic idea here is they are trying to establish this sentence. This page is trying to establish this sentence, and you try to support the truth of this using geometrical consideration. But I'm going to do it differently for you, because I'm going to show you an easier approach to getting the same thing which you will bite in. Okay, to start off with, do you agree? Do you agree? We learned this, right? Now you differentiate this whole sentence with respect to x. If you differentiate left hand side, okay, and then therefore, right, prime of x is equals to 1 over f prime of f inverse x. Let's assume that everything works well. Right? Yeah. Let's assume, okay? Let's Right, so the blue plus the red color, which gives you purple, the purple patch covers what you understand from that page there. So when you see this page, you see purple. Remember, red and blue gives you purple, right? So this page is per page. Right? With this in mind, let's try this question 11. Yo, too fast is it? Sorry. Yeah.
This thing. This thing had took me hours to figure out.
You finished it, yeah?
Uh,
Okay. Kenneth is well ahead. By the way, I also tested you this thing called the in-class exercises though. If you have time to try, you try today. Tomorrow in class you do it. I'll answer a question you have and then we do a graded task. Tomorrow's a graded task, you know, in case of,
GT
yeah, tomorrow is GT1, you know. I'm just afraid that everyone gets full marks.
Why?
Because I think that your class will be able to get full marks for everybody, I think.
Every must get 4 marks.
Why afraid? Then then it could be our test too easy. You know what I mean?
Oh, class 2 is fine.
And then I'll feel very embarrassed to set an easy test for a clever class.
No, this one. This one. Took me so long to figure out this question.
It just need this line.
No, I was doing this, then I forgot about this one. So I was looking at this for like hours and I
Hours,
don't know what to do. Then I just start looking through the notes and I realized.
Okay.
It's not
Okay,
like
for this question 11, read the question. At the onset, I want you to know, some people read the question and they misunderstood, you know. Please don't think that the fx is this value. It's not, you know, it's not. It's not.
then f prime x x.
No, not even f prime x, no. You should see the diagram as like this. There's the graph of y equals to fx.
Yeah, and then a tangent line that's 5.
At this point,
Yeah.
and then from there, you draw the red line.
Yeah.
Let me use this one to draw red lines. Okay, somehow the line is very faint. Okay, delete, not nice. Okay, good, alright. So that's how the graph is like. I hope you can see the fine red line. No? Okay, so how do you do this question? According to what we have proven earlier on, this becomes f prime of f inverse 8. What is f inverse 8? 1. Why is it 1? Because this sentence tells me that f of 1 is equals to 8. So therefore f inverse 8 has to be 1. Then what is the gradient of the function at x equals 1? 1 is here, no? The gradient of this function at x equals 1 is exactly the gradient of this red line. And this red line has an equation y equals to, and based on this equation, okay? Okay, let's do our QCE. Quick chat exercises.
Oh, this one.
Everybody must be able to do number 1, you know. If you are able to do number 1, it means you have learned a lot in this chapter, no? You know what is going on. and I hope it won't let me down. So give yourself the 30 seconds to pen it down, and I'm going to write down as well. Then we can compare to see if we have the same thing. Okay. Then this is too easy for us. Okay. Number 3. If this is a tangent line to the graph, so the value of f1 will be. Anyone wants to tell me what the value of f1? Let's hear from. Okay, Wen Kai. What do you think is number 3, f1? Do you say 1? Right. And the gradient? It's not 2, no? Did we say 2? Minus 2, that's right. Okay, f1 is 1 because when the curve meets the tangent, it meets the tangent at the point in question. And at this point in question, given that the equation of the tangent line is this, so when x is 1, y is equals to 1 as well. Okay. Number 4. So this is differentiability, and this is. So which theorem guarantees us that? No name, no name. So it has no name, you know.
Yeah, I think it's a
What page is that?
Isn't it A-2-8? Yeah.
Right. Okay, 2-8.
Basically saying if the function is continuous, then it's.
No.
A differentiable then is continuous.
Right, differentiable implies. So differentiability
Implies continuity.
implies continuity, but not the other way around, no. The other way around may not be true, no. Okay. So continuity is a necessary condition, but not sufficient. Okay. Okay. So now let's work on this question. When we say average rate of change, it refers to taking the final minus the initial and divide by the interval in question. This is called the average rate of change. What is instantaneous? Instantaneous means evaluating the gradient at the point in question. C. So they want you to actually solve this equation, that the instantaneous rate of change at x equals to c is equals to the average rate of change over the interval. In diagram, it potentially looks something like this now. That this is the point where x is 0, and this is the point where x is equals to pi over 4. Then you're talking about the gradient of this blue line is actually the average rate of change. And what you're trying to do here is you're trying to find the point C where the green line shares the same gradient, you know. This point C is basically trying to do this. Okay? That the instantaneous rate of change at the point C is the average rate of change. And I'm sure if I say go fully digital, Kurtish will be the first to join in the bandwagon. Why not? You like digital notes, right? No, you don't. I'm surprised. I thought you're with me. You're not on my side. Okay, so it looks like there's a lot of resistance. It's quite puzzling. I thought your generation should be all very digital. No? You grew up with the iPad. You look back, your mom will put iPad in front of you when they have meals, so that they won't disturb them, you know, and they have meal happily, and then you have your cartoons happily also.
Back in my day.
Why not? All moms and dad did the same, no? I'm also guilty of that, you know.
I would say because I used to go to school where phones are just straight up not allowed. Phones are just straight up not allowed. And bringing laptop to school had to require permission. So
I see.
so notes I have always been doing on paper.
Huh. No, but when you go out on family gatherings, you just say, nah, take the iPad and behave. And then you will happily receive the iPad in your hand, and then you go to a corner where your cousins, your whoever will not be near you, you can enjoy it all by yourself.
That's the
Not that way?
That's the assumption that the family has iPad.
As what?
Has iPad.
True. But you know iPad can be TV. You know?
Here's the TV. No cable, no nothing, here's the TV.
So this is minus tangent x.
I still remember cable TV.
Why you know? You cannot be by the time you're born, Singapore television already went out. Already worn out by
Not
then.
sure. I used to have satellite TV.
Where?
In Malaysia.
Ah.
We used to have satellite TV.
Okay. You know the StarHub? What are subscriber of StarHub? Used to be Star. Personally, I have done some work for StarHub before. I created their web pages before last time. And because of doing work for them, I was invited to the back end where all their heavy machinery are. There are a lot of satellites there. There are a lot of earth stations, a lot. And then their center, the computer center is all there. Why they invited me in? Because I was trying to firefight something I created for them, software. I created some web application for them. It looks good on Internet Explorer. But when people started using Netscape, in those days there were Netscape. Those days, it went wrong, you know. I tell you. Okay, so I was doing a lot of IT work then.
Does it look like that makes use Chromium now? That's like the base.
In the early days when it first started, if you can code back end, they pay you very well, no? I did some work for Carrier, they pay me $7,000 for it. What you now can do easily with a lot of gadgets, no? But in those days, you had to hand code it, no? All by hand. You must be able to code it and be able to read and write from a relational database. You know what I mean? Yeah. you must also do a bit of database design. Okay, sorry for those bio students who don't really comprehend this. Yeah, I had the skill to do it. So that's why I was able to actually make a bit like that. Okay, now when you reach this stage, right, your x therefore is equals to this magnus, right? You can't do it by hand, you know. Thanks to technology, you can use the calculator. Yeah, don't use calculator. Okay, the answer will be positive value, I'm very sure. Because you want to note something, no? You want to note that actually this is negative, you know. Like this is actually negative. Be very careful, no? I'm quite, you know, lax in this question because I simply just tangent inverse, no? But in solving trigo equation, it's not like that, no? You must solve trigo equation carefully by first and foremost finding the basic angle, then draw the quadrants to see the correct angle that it should be, not just like that, no? This is a bit lax, okay? A bit lax. Okay. Who is good in language? Kaiwan, you're the language person. How to pronounce this word, this name rather?
I have no close theorem.
Some people call it Rolle's theorem, some people call it Rolli. What do you prefer?
Relay.
Shall we just settle for Rolle's theorem? Okay, let's settle for Rolle's theorem.
Spring Rolle's theorem. Yes.
Okay, this theorem is interesting. It says
Oh, icon is on by the way.
yeah, icon is on already. This theorem basically says if you are given a function, and it says that say a function again, a function
Don't do that.
a and b. You should experiment with this, no? Fa and Fb are the same value.
To be honest, Rolle's theorem is just an expansion of mean value theorem.
Special case.
Yeah, it's a special case.
Yes.
It's a special case. It's just one part of it. It's not even like special case. It's just one part of it. True.
So the thing is, between these 2 points at A and B, now you try. Can you draw those 2 points using a continuous and differentiable curve without lifting up the pen? Can you lift up? Can you take a pen and try to join A to B with a continuous and differentiable? Differentiable is sometimes described as smooth, no sharp corners. So no matter how you draw, right, you'll find that they become to a certain point in time that you need to actually turn nicely. At this point, when you turn nicely, at this point the gradients will be 0. No matter how you do it, you know, as long as you want to draw a continuous and differentiable function. So it must be continuous on the closed and differentiable on the open interval. You're feeling too cold? You can off the fan. Okay, number 13. Could I challenge you that for number 13, you start off sketching the curve? Let me go around to see who cannot do it here. 13. Sketch the curve for 13. Let's see who cannot do it. Why is something alone behind? The other people is draw the graphs. Yep, right. Studying chemistry, my lesson. Good grief. What happened? Where is it due? Trevor, where is it due? Yesterday.
Oh, that's problem.
Let me see your graph. Okay, good. Your graph, please. Okay.
Be like me, do math over here.
Right. Okay, I can see that quite a lot of you can draw the graph. Hey, there's the girl who's there, right? Where's the girl now? Sick.
Okay, then it's a big
Oh, no, she's here. She's sick, is it? Oh, she has COVID. Okay, finally. Let's face it, it's a matter of time everyone gets it. I got it.
That sounds like the sports F dot thing. You got COVID finally.
My daughter got it twice. Huh? She's fine now, yeah. My daughter's not vaccinated. Yeah. Okay, so I saw that quite a number of you can sketch a graph. So first and foremost, this function is obviously continuous on 2, 3, since it is a polynomial.
F is continuous because it's a polynomial. F is differentiable because it's a polynomial.
Right. Okay, thanks, Kenneth.
Because it is a polynomial.
Thirdly,
F2 equals to 0, which is equal to F3.
Equals F3 equals 0.
So it satisfies all three conditions, the Rolle's theorem applies.
okay, so by Rolle's theorem, there exists C element of such that f prime of C is equal to 0. So what you do is you now do f prime of C equals 0. This implies that 2C minus 5 is equals to 0. Okay, let me ask Zoe, you know why 2C minus 5? I'll give you another 30 seconds. Why 2C minus 5? Think of f prime and think of fx. Some more? Okay, yeah. We simply differentiated fx too. I differentiated fx mentally and putting x and c. Right? Interesting answer. It was given to me. Okay. So, how many values of C do you have? There's only one value of C. So in this case, this is a trick question. Okay. In exam, don't write RT. Spell the name of the theorem as Rolle's theorem. Yeah. You all chose your own sitting position, is it? Or assigned by Mr. Lim Chong Shen? How does he decide?
No, I think he does. Okay, the groups were divvied out randomly. So the group of students, there are like 6 groups. The groups of students were divvied out randomly. Then the group chose which part of the classroom to sit.
Oh.
Then the sitting also chosen by the student.
Okay.
Only exception is me. Because Mr. Lim doesn't want me to sit here.
Oh.
Because Mahir asked me to sit here. And the Mr. Lim does not want me to sit here, it's not here.
I'm also here.
Okay. The next one is the so-called mean value theorem.
More general case of the rules.
Geometrically, right? if I got magic power and I tip it straight, it looks like a rose here. You know what I'm saying? Yeah. If I got magic power, I can change this. This concept is not new. It was discussed in the earlier example. Remember, the average rate of change is equal to instantaneous rate of change.
Oh, but that's zero. So now it's
In the case of Rose theorem, it's 0 billion. But for mean value theorem, which is more general, it says here, okay, that the gradient of C is equal to the gradient of the two endpoints A and B. And they have the same condition, no? Continuity on the closed and differentiability on open. The good thing is you don't really need to do the proof, you just need to know how to use it. Okay, this question, part A. Okay, so again, part A, right? F is continuous on because square root is a continuous function and x plus 2 is a polynomial function, and f is differentiable on 2, 7 by MVT that exists C element of 2, 7 such that f prime of C is equals to then this implies that f prime of C, how much is f prime of C? Is 1 over C plus 2. What is f of 7? Is 3, and then minus 2 is 1, and then the denominator is 5. So I did some arithmetic mentally. I'm sure you will get the same thing. So therefore, C is equals to 17 over 25, is it? Check my calculation. I could be entirely wrong, though. Oh, I think it's very wrong.
I got 21 over
4. 21 over 4, right? Sorry about it. My arithmetic fails. Okay. That's actually part A. Even it's very obvious, you still want to state the condition of that function f is continuous on the closed and differentiable on open. Because if you don't state, right, the author or the marker may not know that you know these are conditions needed. And it's always good to state the name of the theorem.
Minus 8. It's 17 over 4. Minus.
Okay, that was commercial. Testing alertness. Thank you.
Yeah, I was calculated to be. I was 17 over 4.
17 was right. The
I was
percent is right.
looking at my number and be like,
Yeah,
Sorry. We are trying to trick all of you.
Wow, right here.
Yeah,
Right,
two of us trying to
coalition
trick
with
all you.
Come on. Can I finish it? No, I only have 8 minutes. I can finish.
Okay, so that's part A. We will end here, okay, so that you can go for your lunch now, because I'm afraid that I'm going to rush if I do. Okay, part A. You'll do part B the next time. So bear in mind, tomorrow come prepared for the great task one,